Hi, welcome. I'm trying to learn electrical engineering, today the volt, and after we've done it, we're going to do leg injury prevention training. And if you participate in the leg injury prevention training, then this is on this. The volt. In a previous volume, it was explained that work is measured in joules. I don't have a previous volume, this is basically part 1, but we read the beginning already in the last part of potential differences. Now, a joule is the work done when a force of 1 Newton moves its point of application through a distance of 1 meter. Out of words which I basically don't understand. Let's look at that. A joule is the work done. So a joule is the amount of power which was done. When a force of 1 Newton, we're having an amount of 1 Newton, moves its point of application through a distance of 1 meter. Okay, the joule is the amount of power needed to bring an amount of a unit of Newton over to another point. When work is done at the rate of 1 joule per second, this is said to be the power of 1 watt. I came a couple of times across this 1 joule is 1 watt, but I don't really understand why are not both needed if there's so much the same. Okay, whatever. And if you're working, the joule is the amount needed to put 1 Newton of something over to the other place. Newton seems to be an amount. We're needing an amount, joule is measured in it. And if you're working with a power of 1 joule to bring it over to the other side, we're working with 1 watt. A volt is defined as a potential difference which exists between 2 points when a column of charge passing between those points does 1 joule of work. Okay, column is another thing, measurement of electricity. Okay, we're having an amount of 1 column of energy, and we bring it over to the other side over a specific distance in a specific time. And the volt is the amount lost at electrical current if you're working with 1 joule to bring this 1 Newton, which is a column, over to the other side. Because 1 joule per second is a watt and also 1 column per second is an ampere, we can reword the above statements for this again. Because 1 joule per second, so we're working with 1 joule, that's our strength, we're working with 1 joule. It is 1 joule per second is a watt, and also 1 column per second is an ampere. And if you're working with 1 second on 1 column, that is an ampere. Now with the third thing, it's just the same. We can reword the above statement as follows. A volt is defined as a potential difference which exists between 2 points when the current of 1 ampere does work at the rate of 1 watt. Okay, we're working with our power on level 1, what's called on like a car driving in the first gear. In the first gear, we're working with gear 1 to bring 1 ampere of current of electrons over to the other side. And what we're losing while we're doing that, as our work, is 1 volt. And because this is chemistry and physics and is every time the same, we can define that as a volt. And not just that was sounds so effortsome to do it, but you can just directly say it is a volt. Both these statements defining a volt, although differently worded, mean exactly the same thing. It means we haven't really understood twice the same thing. They make it clear that the power or rate of conversion of energy associated with the current depends directly on the potential difference associated with it. They make clear that the power of energy associated with the current is associated with the current. We're saying the volt of this sounds so high as much as is lost. Now just the thing at the side. Just as if it's maybe the point we want to make. If you're having what they call these things which delivers electricity from one point to another one, maybe it's just about that. We have to know how much is 1 volt and how much is lost, so we can transfer the current of electricity from one tower to another one. We have to know how much is lost if we bring 1 ampere over. And therefore we have to have all these different things. We have to have the ampere, so we know how much is coming over. We have to have the volts, so we know how much is lost. We have to have watts, so that we know how much pressure is on it. And we have to have a joule, so that we know how much time it takes. Whatever, something like that. Maybe it's about that. Maybe it is actually that we need all of these 5, 6 different things just to measure the electricity. Because we don't just have to know how much is transported, but also how much is lost. How far the electricity would reach, because if we don't have enough pressure against it or whatever, then it doesn't come through the cable. So we need to know how long the cable is, how much pressure it has, and on one... I don't get it, but I think this is what they want to tell us. Expressing this fact mathematically, so that the power of an energy has to do with the difference of which the power loses from one point to the other. It makes a bit sense. The power a baseball has to hit something is dependent on how far it was thrown. Not just how hard it was thrown, not just in what angle, but also how far the ball has traveled until it hits something. That makes sense. And we have to know it makes sense so that we know how much, whatever we now need, how much, I don't know, to bring the electricity from one tower to another tower, we have to know that. And that has to do with the amount. And this fact is when volts multiplied with ampere equals watts. And the volts is what we're losing by bringing it over. The ampere is the amount we're having to transfer. And watt is what reaches after having lost what we wanted to transfer over. I think we're getting closer. It could be a bit completely confusing at all, but I think we are setting the framework. We're carving the puzzle pieces or the jigsaw pieces, and we can later puzzle them together. Now, is it now puzzle or jigsaw? I think the expression is puzzle. It's puzzling something together. Now, the expression is puzzle something together. Why is not the game called puzzle and jigsaw? Another thing here. Example: the mains supply applies a potential difference of 250 volts to an electric fire, whatever it be, and the current of 4 ampere flows through the fire. Let's do it again. A mains, I don't know what a mains is, whatever. A machine applies. A main supply applies. A main supply. Okay, just a machine is supplying a potential difference of 250 volts. So it's going to lose 250 volts while going through the potential difference to an electric fire, and the current of 4 amperes flows through the fire. Okay, we're having 4 amperes, and we're bringing it with 250 volts over. And what is the power consumption? How much energy is converted to heat in 1 hour? And that is 250 volts, because that is what is lost during the potential difference thing. Times the 4 amperes, and we're having pushed through 4 loads, what is it called? 4, what the truck is loading. 4 lorries. And we're having put through 4 boxes, and 250 items were taken out of each of the 4 ones, so we're having lost 1,000, and that means that thing needs 1,000 watt. What we're having running in between the potential difference, which is making our electricity, fire and heating, whatever, or boiling eggs. This rate of working is called 1 kilowatt, because we're having 1,000 watt. That makes sense. 1,000 watt and 1 kilowatt. So this rate of working is 1 kilowatt, when 1,000 joules of work is done every second. And a joule was now the amount of the force to bring 1 Newton of application for a distance of 1 meter. A lot of things here. As there are 3,600 seconds in an hour, work done in 1 hour are 3.6 million joules. So this is what we don't just really know what joules are. For convenience, a rate of working of 1 kilowatt, which is maintained for 1 hour, is called a kilowatt hour, and is equal to 3,600,000 joules for energy work. 1 kilowatt hour. I understood something else. The 1 watt is just 1 watt, and 1 kilowatt is 1,000 watt. And now 1 kilowatt hour is 1,000 watt after 1 hour. 1 kilowatt hour, that is 1,000, 1 hour long, 1,000 watt onto something. And 1 watt is 1 joule we're bringing from one place to another one. And what do we know? What is with column and the ampere and the no, I'm wondering if we understood it or not. Well, I'm wondering if we understood what it wanted to tell us, because we were not really here to explain us what an ampere, what it was, and the other thing is. No, I think we understood what we wanted to say. We just don't understand what was all used there. But I think that is no problem. I think we can continue while we're working on finding out of what now these 5, 6, 7 different scales are which we're using all the time. We haven't understood them in the basics. We know we have something to do with pushing something over, how much the push is, how far it comes, how much is lost while pushing it over, how heavy the thing is, how much more is transported over, and how much is taken away, and how which water is taken away is now how much in 1 second, how much in an hour, and how a better term for it is in kilowatt hour. I think we understand the framework. We have our puzzles basically, and now we're gonna go on for the next parts and look if we can maybe puzzle together what we have. That was the actual electrical engineering part. If you were here for electrical engineering, you can go directly to the next part of electrical engineering. You will do now the leg injury prevention training. If you stand participate in the leg injury prevention training, then it's with the arms. Good and standing leg, good and standing leg, and the other legs are flexible in the air, swinging it to the side and the front. And the other foot swinging it around to the side. And one foot bring it in front and back. And the other foot bring it in front and back. And now bring one foot up, pine pilcher, breathe in, out leg to the side, again in, out into the middle, down, other leg up, breathe in, out to the side, again in, out into the middle, and down. And now breathe in, arm up, hang up with the arms over to one side. And over to the other side. And now with the arms over to one side, and the knee also over to one side. And chin. And then down, other leg up, go over to the side of the front arm. A little over. And change off. And off. And down. And now stand on one leg, turn, this exercise can go to the knee, turn over to the knee, go down into the knee, over to the other side, come up again. Then again, stand good, turn over to the leg, go down, over to the other side, come up, upper leg, stand good, turn over to the leg, go down, over to the other side, come up. And again, stand good, turn over to the leg, go down, over to the other side, and come up. Another clock can go again onto the front, always down with the knee and with the other leg, always in 90 minutes intervals to the what? To the digits on the clock. I don't know. The other foot, bring it in front, and to the other side. It's 9. It's at 7:30, 6, 4, and 3, and also the 1:30 and 3. And now we'll be bent. Good standing leg, upper leg with the heel onto the ground, and lift the heel off the ground, press again on the ground. And upper heel onto the ground, and lift the heel off the ground. And now, one leg up, and down, stand. And upper leg up, down. And upper horse, leg in, and back, and again in, and back. The other leg in, back. And over camel you can do the horse roll if it's too complicated. And now the upper part of the body comes also down, and the other leg. And now you can do the rest, stamp, horse or camel. On our one, you swing the leg completely back. Try to be tall in the standing leg, and try not to fall over. And try not to fall in the abdomen. And training the leg. And standing, feel breathing in, come down. Breathe out. Breathing across the legs. And breathing out. Now, that was the leg injury prevention training. I thank you very much and have a nice time.